We have learned how to differentiate a polynomial, so let's continue learning some more differentiation rules so that we can leave the limit of a difference quotient definition of the derivative in the background. We're going to go ahead and introduce the derivatives of exponential functions so that we can start working problems with these type of functions, but we're not going to be able to prove these derivatives until later in the semester. So we're just going to state them as facts, and we will prove them once we have the mechanisms in place to do so. So recall that an exponential function is of the form some fixed number raised to a variable x, and we need a to be either between 0 and 1 or between 1 and infinity. So we get two different graphs based on whether or not the base of our exponential function is greater than 1 or between 0 and 1. But in particular, a can't be negative and a can't equal 1 because the function 1 to the x is not very interesting and does not behave in an exponential manner. Okay, so the derivative of our exponential function a to the x is, okay, so we get the whole exponential function back, and then we get a coefficient that's the natural log of the base. So this is just a constant. The natural log of a number is just a constant. So this coefficient is a constant. Sometimes we forget that the natural log of a is a constant. All right, let's work a few examples. Let's find the derivative of 2 to the x. So the first thing we get is the whole function back. So we get 2 to the x, and then we just multiply by the natural log of the base, and the base is 2. And that's our answer. If we're doing some sort of application problem, we might want to look up some approximation for the natural log of 2, but in general, unless we need an approximation, we just leave it as the exact value. All right, let's work another very important example. So e is the most important base to have for an exponential function. So here we get the whole function back times the natural log of the base. Now, remember that the natural log function and e to the x are inverses. So remember that means natural log of e to the x is just x. Natural log of e to the 7th power is 7. For this expression above, the exponent is 1. So natural log of e to the 1st power is just 1, right? So this constant here is 1. So this derivative is just 1 times e to the x, which is e to the x. So very importantly, e to the x is the function whose derivative is itself. So if you think of that in terms of the slope of the graph, it means that at any point on the graph, the slope of the tangent line, so the rate of change of the graph, the instantaneous rate of change of the graph at that point, is itself. So let's just work a quick example. Let's find the equation of the tangent line at x equals 2. Right, so there's our tangent line. Let's find its equation. Okay, so let's find the equation of the line tangent to e to the x at the point x equals 2. So to find the equation of our tangent line, we need two things. We need a point, and we need a slope. The point is going to be 2 and then f of 2, plugging 2 into our function, so that's e squared. The slope is the derivative at 2. All right, so to finish finding our slope, we need f prime of x. Well, we know that f prime of x is just the exponential function, and so f prime of 2 is just plugging in 2 to that function, so we get e squared again. So the derivative of the tangent line is y minus y1 equals the slope times x minus x1. And there it is, and again, we usually write this in point-slope form. E squared is just a constant, so that's our slope. So minus 2 times e squared plus e squared, and of course these are like terms, so we can combine this to 1 e squared. And let's just quickly graph both the function and the tangent line on Desmos to make sure that this is a reasonable answer. Okay, so here's the graph of both our function e to the x in red and the tangent line e squared x minus e squared in blue. A couple things of note. E squared is about 7.3. You can use a calculator to estimate that. So you can see here that the y-intercept of our tangent line is going through negative e squared, approximately, right? That's an approximation, but it looks like it matches, looks like that's correct. Looking at the graph isn't a rigorous formal check of our answer, it's just sort of making sure it's at least within the realm of reason. And then the other thing we need to make sure of is that it goes through the point. It goes through the point, let's see if I can get it on here, to e squared, and again, there it is, and that the tangent line looks like it's tangent to the graph at that point. So let's see if we can just zoom in a little bit and just confirm that it looks like it's tangent at that point, and it does. It looks like the tangent line is a really good approximation of the actual function at that point. Okay, so our tangent line looks like it's a very reasonable tangent line to the graph at that point. Let's check in where we are so far. So far we can take the derivative of x raised to any constant, it doesn't have to be a positive integer, any real number, and we know that that derivative is just n times x to the n minus 1. And we know how to take the derivative of an exponential function where we have a constant base and a variable in the exponent. And this is just the natural log of the base times the whole exponential function. And we also know how to take the derivative of a constant. That one's very simple, right? The derivative of a constant is just 0. And then for any of these, we know how to take the derivative of sums and differences, or a constant multiple of any of these. Okay, so given any of these, and then a sum, a difference, a constant multiple of them, we know how to find those derivatives. What we don't yet know how to find is the derivative of a product of these types of functions. Except for the constant. We do know how to find the product of a constant in one of these functions because then it becomes a constant multiple. But if I were to take the product of any other functions, we don't yet know how to differentiate them, so let's learn that rule now. So the product rule says that if f and g are both differentiable functions of x, then their product, f times g, is also differentiable, and the derivative is given by the following. So the derivative of the product is the derivative of the first function times the second function plus the first function times the derivative of the second function. Let me write that without the parentheses x just to make it a little easier to see. There's a whole lot of parentheses in that above expression. So the derivative is the derivative of the first times the second plus the first times the derivative of the second. So we'll prove this and work some examples, but notice that the derivative of a product is not just the product of the derivatives. So it's not as nice as the sum rule where we can just take the sum of the derivatives individually. Here there's a little more to it, and we'll see why when we go through the proof. Let's prove this derivative. So we need to use the limit of the difference quotient. So our function is f times g, and then we plug x plus h into that, minus the function by itself, just fg of x, all divided by h. And now we can use the fact that if we have a product of functions, we can simply separate that and evaluate their product after being evaluated at the input. That's kind of a wordy way to say what I'm writing, but I hope that that makes sense. Feel free to ask if it doesn't. All right, now what? Well, sort of working backwards from where we need to be motivates us to add the following well-chosen form of 0. So I'm going to add and subtract the same quantity here. Again, why am I doing this? Because I'm working backwards from where I know I want to be. So minus f of x, g of x, all over h. And now I'm just going to regroup this. So I'm going to split this into two sums, and I'm also going to factor out the common factor from each sum. And so I'm going to factor out f of x plus h, and then I'm left with g of x plus h minus g of x, and then that's all divided by h. And then the second part, so I'm splitting the fraction into two pieces and simultaneously factoring out a common factor. So in the second half, I'm factoring out g of x minus f of x, and then all over h. And then we know that we can split that limit into two pieces, right? The limit of a sum is the sum of the limits. Okay, so I've added the last line here, so you didn't have to watch me write. And now we're prepared to take the limits, right? So here, as h goes to 0, f of x plus h goes to f of x plus 0, which is just f of x. And look closely here, right? What is that limit? That's g prime. Oops, wrong color. That's g prime of x. That's the limit quotient for g. And then in the second half, we have the limit as h goes to 0 of g of x is just g of x. And then again, this second portion, that's the difference quotient for f. So that's f prime of x. And that's what we were trying to show. So that establishes our theorem. The derivative of a product is equal to the derivative of the first function times the second, plus the first times the second, the derivative of the second. And of course, addition is commutative, so it doesn't matter which one of these pieces you put first, as long as you combine the derivative of one piece of the product with the original function of the other. Let's work an example of using our product rule. So you might notice that here we have a function and it is written for us as a product. We could multiply this out and it would be a polynomial, and then we could take the derivative just using that, what we already know. But multiplying this out looks pretty unpleasant, so let's go ahead and use our power rule. So if you want to name the pieces of the function, you can. Our overall function has been named f, so we can call this g and this h. And then by our product rule, the derivative is just g prime h plus gh prime. Again, it doesn't matter which of these pieces you put first, because addition's commutative. And if it helps you, you can sort of write this out. Let me scoot over left a little bit. So it's going to be the derivative of the first piece times the second piece. And you don't have to write all this out. I'm just being very clear the first time we go through this. And then we add the first function times the derivative of the second. And you should be able to pause here and go ahead and take these, the two derivatives that we're going to need, since they're both polynomials, right? So we need a derivative here and here. So pause and find those derivatives using the techniques that we learned in the previous video. Okay, so this is 6x plus 6, and then the derivative of 1 is 0, so that term goes away. And then this second piece stays unchanged. And then the first piece stays unchanged. And we take the derivative of the second piece. And here we get, okay, so our exponent becomes our coefficient, and then we multiply that by the constant multiple to get 700 x to the 99th power. Again, minus 250 x to the 49th power. And then, let me fix that 9. And then the derivative of x is just 1. And that's it. That's our derivative. Now, if all we're doing is practicing the product rule, we could leave it like this. Sometimes the homework system asks you to multiply it out, unfortunately. And if we were going to be doing more with this function, if we were going on to solve an additional problem, then we might need to multiply it out and write it in a nice polynomial form of decreasing powers, but unless we need to do that, this is a fine way to leave it. Now that we have the product rule, let's state the quotient rule. So it says that if f and g are differentiable, then so is their quotient, f divided by g. And the derivative of the quotient is given by the following formula. It's the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator, divided by the quotient of the denominator squared. And of course, anytime we have a denominator, we need to clarify that g is not 0. We're not going to prove this because the proof is very similar to what we did to prove the product rule, where we just add a certain quantity and then we regroup everything and end up with this formula. So there's really nothing new to see as far as the proof. So we won't spend time proving it, but if you're interested, you can always try to prove this yourself, and then you can look it up in many places or reach out to me if you have questions as you're trying to prove it. Now, something to be careful of with the quotient rule is our numerator has a difference in it, not a sum. So in particular, the order matters. Which piece is differentiated first makes a difference. So it is the numerator that gets differentiated first, and then the denominator gets differentiated in the second term. There are lots of mnemonics that can help you remember this formula. Some of them are super annoying, so I will not introduce them to you, but feel free to look them up if you're having trouble remembering them. I know when I was an undergrad learning this formula, I just remembered that the first term looked like the word fig if I added a little I in there. So whatever works for you to help you remember it, just be conscious of the fact that the order matters in the numerator. Let's work an example of using our quotient rule. Let's find the derivative of the rational function fx squared over 4x plus 3. As we find this derivative, I'm going to use color just to see if that is helpful. So we're going to find first the derivative of the numerator times the denominator minus, very important, subtraction, not addition, minus the numerator times the derivative of the denominator. Let me squeeze that there. All over the denominator squared, not the derivative of the denominator, just the regular old denominator squared. Before we finish finding this derivative, I want to show you a really common error. I'm concerned that if I show you this error, you might remember seeing something like this and not know if it's right or wrong. So before I show you something wrong, I'm going to put these skull and crossbones on the screen so that you'll remember them. So if you have a visual image of this error in your head, hopefully it will be accompanied by these images that let you know that it's wrong. So here's what people do sometimes that's very wrong. They cancel this term with 1 power of the denominator, and that's bad algebra. My denominator is supposed to divide the entire numerator, not just the first half of the numerator. So if you can't factor it out of both terms of the numerator, then you can't cancel it with the denominator. So be careful with that algebra error, and if you have questions about that, please reach out to me. Okay, so let's go on with what we are supposed to do in this problem. So we take the derivative of our numerator, just using our power rule together with our constant multiple rule, and we multiply that by the denominator minus the, I guess I don't need parentheses there, minus the numerator times the derivative of the denominator, that's just 4, and then that is all over the square of the denominator. All right, so we've done everything we need to do with the distinguishing between the numerator and the denominator, so I'm going to go back to a single color as we multiply out our numerator to see if we can combine any like terms. So 20x squared all over, and I don't have any need to expand that denominator. I'll just leave it like that unless, again, there's some reason to expand it and there's not. But I can combine the like terms there and end up with our final answer of 20x squared plus 30x over 4x plus 3 squared. A question I'm commonly asked is whether or not we need to factor out the GCF of the numerator. That would be 10x. And the answer is no, you don't need to factor it out unless you're trying to cancel with something in the denominator. But there's nothing that's going to cancel here, so you can just leave it alone and go on to the next problem. Let's move now to talking about higher order derivatives, and there's really not much to say. A higher order derivative is just a derivative of a derivative. The only thing that's really new is the notation. So let's just take a look at what the notation is. So if we have our original function f, we know how to write the first derivative. There's the second derivative. So let me note this second derivative, and we'll do Leibniz notation in a second. So there's the second derivative. The third derivative is 3 hash marks, and then we stop with the hash marks. So third derivative, because nobody wants to be counting, too many hash marks. So after the third hash mark, we put a 4 in parentheses, and the parentheses helps distinguish it from a power. So it's not f raised to the 4th power. The parentheses means we're taking the derivative. And then for any number greater than 4, integer greater than 4, you would just use parentheses to denote that derivative. And I went ahead and completed that table there. So let's go ahead now and take a look at what the higher order derivatives look like for Leibniz notation. So we know the first derivative. Let's just assume f is a function of x. For the second and subsequent derivatives, the superscript notation is just a little unexpected. So it's d2f, and then we write dx squared. And then so on. There's nothing that changes for the higher order derivatives except that single number. So dx cubed, and then the last one on this list. Of course, we could go on forever. Right, so there it is. So there's the notation for Leibniz. The first superscript is between the d and the f, and the second is after the variable in the denominator. So let's work an example of finding a second derivative, and we've picked an example that's going to require us to use several of our differentiation rules to get through it. So to find the second derivative, we have to start by finding the first derivative. So first we'll find the derivative of 4 to the x over x. And as we look at this function, we see that it's a quotient. The numerator is an exponential function, the denominator is a polynomial, but overall it's a quotient of two functions, so we use the quotient rule. So we have the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator all over the denominator squared. And if you don't need to watch me do this, please pause and finish this on your own. So our numerator is, we take the derivative of 4 to the x, and we get the natural log of the base times the exponential function, all of that times x, minus 4 to the x times, now the derivative of x is just 1. All right, so our derivative, I'm just going to rewrite some of the terms. X times the natural log of 4 times 4 to the x. And I just moved that down so I wasn't running into the previous line. Minus 4 to the x over x squared. There's our first derivative. And my suggestion for you when you're working a problem like this that's lengthy is to double check each line as you go. You don't want to get to the end in a few minutes and then figure out there was a mistake on the first couple lines. So just double check each line as you go. Okay, so now to find the second derivative of 4 to the x over x, we just have to find the derivative of the first derivative. So we just take the derivative of the expression we just found. Okay, so moving forward with this derivative here, again, we have a quotient. Right? Again, the overall structure of this function is that it's one function divided by another. So we're going to need to find the derivative of the numerator. Numerator is a little more complicated this time, but not something we can't find the derivative of. So the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator. Almost fits. Derivative of the denominator, and then all of that over our denominator squared, so x squared squared. Okay, so when we find this first derivative for our quotient rule, let's write it out in green just to keep track of it, because notice that this is a difference of two functions, and then within the difference, the first term is a product. And notice it's a product of two functions, because natural log of 4 is a constant. so we don't have to treat it like a function. Okay, so we need the product rule for that first piece. So we have the derivative of the first times the second, and I'll just call the natural log of 4 times 4 to the x the second function, plus the first times the derivative of the second, and I'm just going to use a bracket there. You can use whatever notation there works for you. And then minus, by our difference rule, right, the derivative of that second term. Phew, that's just the first piece, okay? And then we multiply all of that. We multiply all of that by x squared, and we continue. Okay, minus x times the natural log of 4, 4 to the x, minus 4 to the x, all of that in parentheses, and then that gets multiplied by the derivative of x squared. By our power rule, the derivative of x squared is just 2x. And then that's all divided by x to the 4th. Okay, so we still have some functions that need to be differentiated in our expression. There they are. Let's take care of that now. So this is, the derivative of x is 1. So we're just left with the natural log of 4 times 4 to the x plus x times, and now we need to take the derivative. Natural log of 4 is a constant. So by our constant multiple rule, it just stays the same. It just comes outside of the derivative of that expression. And the derivative of 4 to the x is the natural log of 4 times 4 to the x. And then we subtract the derivative of 4 to the x, so natural log of 4 times 4 to the x. That's all multiplied by x squared. Maybe I'll switch to a bracket, to a little bracket there instead of a parentheses, so x squared. And then we still have to subtract the rest of the numerator. Boy, who picked this problem? I'm going to multiply this through. So I get minus 2x squared times the natural log of 4 times 4 to the x plus 2x times 4 to the x. So notice I distributed the negative sign here. And all of that gets divided by x to the 4th. Okay, that numerator is a mess, so it's worth tidying up, but we're done taking derivatives. We've done the calculus, if you will. Now we're just doing some algebraic simplification. The first thing to notice is that we can simplify a power of x because the first term has an x squared term, that has an x squared term, and that has an x term. So from the 3 terms in the sum, in the numerator, we can factor out an x, and so we can simplify that with the denominator. So what that's going to look like is this term becomes x, that term becomes x, and then that x gets simplified, and in our denominator we now have x cubed. Okay, so once we distribute this x through to each term, and then write out the rest, we see that we can't cancel any more powers of x because this last term does not have a power of x in it. However, we quite unexpectedly do have like terms. Do you see that these two terms are like terms? So we have negative x and then negative 2x, both times the natural log of 4 times 4 to the x, so we have negative 3 of them. And then over here, we've got another positive one. So we have negative 2 of them. And that's a pretty useful simplification, right? It's important to do those big, obvious simplifications. Now, if we wanted to, we could factor out a power of 4 to the x from each expression, but we don't have to. That is not something that's, going to be this major simplification. That's just, we could write it another way. And in the future, it will often help us to write things as products so that we can then continue working with them, but it's not required. So you can leave it like this, or if you want to factor out 4 to the x from the numerator and then write the rest, you certainly can do that too. So I'll leave that up to you. And then all over x cubed. So it took a while and it stretched the capacity of my screen, but we found the second derivative.